We're going to continue our series of lectures on training neural networks. So here's where we were at the end of the last class. Get your name tags out, please. Yeah. We saw early on in the first week that neural networks are universal approximators. They can, in principle, approximate anything, but they must be trained to do so. Do you have your name tag? No? Okay, tell me your name. Kishore. Kishore. That here, everybody is Kishore. Please stand up and tell everybody your name.
I am Kishore.
Thank you. Right? And if you don't want to be called out that way, if I come your way, then you better have your name tag out. Okay. And then we said that neural networks must be trained to approximate anything. And the way we train it, we know what we want them to compute. And we must adjust the network parameters to compute whatever it is we want them to compute. So here is the key piece that we must remember. If I can get a chalk. Does anybody see a chalk here? Yeah, here's one. This is the bit that we're going to hang on to for a bit. That I'm just assuming a single dimensional input for illustration's sake, but we know that this is multidimensional. And you have some target function which is unknown, g of x. And the network itself computes some other function which depends on the current set of parameters. And what are we trying to actually do when we train the network? And what is the loss?
The difference between the actual function.
That is not the loss, right? So what we are trying to do is to minimize this area. Is this the divergence, or what is this? Mm-hmm. What did we say this was when I wrote it down? So, yeah?
The integral from across the whole domain of the divergence.
It's the expected value of the divergence, that entire area. So this is the f of x is what the network computes. G of x is the function that you're trying to estimate. And our intention is to minimize the area, the difference between the two. But then what do we actually minimize? Maria?
Is it like between the proxy of the function itself?
Is that the proxy? What else? So can you tell me, what do we actually minimize?
The average of the sample divergence.
The sample divergence. So we don't actually have this entire function. We only have, and we cannot know it in most cases. So what we have is a bunch of training samples. And at each training sample, you have, please do not slide, you have a gap. And so we try to minimize the length of these lines, right? The average length of these lines. And the intention and the expectation here is that if you minimize the average length of these white lines, you're going to minimize the function you estimate will also minimize the shaded area, right? So, and the way we do it, the average length of these lines is a function of just the network weights. And so this average length, what did we call that? Somebody gave me the term earlier. Himash, what do we call it?
Empirical error?
Empirical error, but somebody else gave me the name. The loss, right? The average length of these lines is the loss. When you minimize the loss, are you actually minimizing what we really want to minimize? No, right? So, but we hope we are. And so the loss is what we minimize. And we do so using gradient descent because it's an ugly function of the network parameters. And we found in the last class that vanilla gradient descent can have all kinds of issues. So better convergence methods, it may not converge at all, it may bounce around, it may get stuck in bad places. So better convergence can be obtained through methods that normalize variation across dimensions. We like to have large learning rates in the beginning that decrease over time, and coupling the learning rates in the various for the different components can be disastrous. So methods like RPROP that decouple the dimensions can improve convergence. And lastly, we just touched on it, momentum methods which emphasize directions of steady improvement and de-emphasize unstable directions can give us benefits. So this is where we are, and we are going to move on. We're going to be talking about incremental updates. We will revisit trend algorithms, and in the next class, we're going to go over some of the issues that affect how the model learns things and how we can improve the manner in which it learns the function that it must. So let's look at incremental updates. Here again is the problem. Keep in mind that what we really want to minimize is that shaded area I have on the screen. But what we're really given is a bunch of input-output pairs at a number of locations. And based on these, just on these few training samples, we want to estimate the entire function. So here's what we did. We started with an initial guess. Regardless of the fact that we want to minimize the shaded area, let's focus on the fact that we are just minimizing the loss, which is the average divergence across the few training samples that we do have. And so when we do that, this is what gradient descent does. We start off with an initial function. This, when you initialize your network parameters, it's going to compute some odd function shown by the dotted red line. And this initial function is going to be lower than the target function at some training locations, and it's going to be higher at other locations. And so we're going to adjust the network parameters to minimize the error over the entire training set, which means that our adjustment will attempt to increase the value of the function where it lies below the target value. So it would try to increase the value of the function here and here and here, and decrease the value of the function here and here. So you adjust your network parameters minimally. And when you do that, you get a new function. And then this new function has errors again all over the place. And so once again, you're going to adjust the network parameters to reduce the error at every training location. So to increase the value of the function where it lies below the target and decrease it where it lies above the target. And we keep doing this until we converge. Now this is what we want to do. So there are two steps here. The first is what we really want to do is to minimize the shaded area, but instead we're minimizing the average divergence. And even so, what we want to do is to minimize the average divergence over all of the training samples, because that's the closest you can do to actually minimizing the shaded area. Now this is what we call a batch update, where you're considering all of the training samples, the total error over all of the training samples, and this is what we minimize. And when we do so, it's adjusting the function at every training instance. So here's your first pull. Seconds. Is it 60 or 90? Was it 60 or 90? Maybe 90. There's students in Kigali. So you have 90 seconds for the polls. Students on Zoom requested more time, so we will wait a bit. And then I'm just going to walk down here and pick on random people. Today, I'm going to focus on people at the back of the room, and you will answer the options. Okay, that's Isaac is the first option, right? Yes. And what about the second?
I think so as well.
And Uma, what about the third?
Yeah.
And Dhruv, the fourth? Okay, so the actual loss function we try to minimize requires batch updates. And they minimize the total loss over the entire training data. Now, the batch updates optimize, again, the first and the third statements are the same thing, right? But they require processing the entire training data because you want to get the average error over the entire training data. What could the issue be with this? Arihan.
Not sure.
So, Shrey, what could the issue be with this?
You're not going to actually use the shaded area, but you're getting approximately.
There's something much simpler, right? You're going to have to process the entire training data. What is your typical training data size? Is it small? Is it large? Is it in tens or is it in billions? It's tends these days to be in the billions. Do you really want to do this? Wait to process until you processed every single training instance before you update? It does not make sense, right? So what would you rather do?
Mini batch.
So what is the notion of a mini batch, right? And why? That's what we're going to look at. So what you would rather do is to just, you can think of data as just coming in continuously. And as you see data, you would like to update your parameters. An online process makes a lot more, computational sense. But then will that actually converge? Yes, Virginia.
When you say actual loss function, are we still talking about the individual data points? 'Cause
Yes, the loss I said was the individual data points. I distinguish, correct? I did make the distinction, right? So here's what we can do instead. Let's go to the other extreme. Think of this, I like to use this, metaphor of trying to make a shape out of putty. Now, there's some target shape. You want to make it look like a landscape or a doll or something, and then you have a lump of putty. In the ideal world, you just sprout a whole bunch of arms, like a typical Hindu god, and then you'd be adjusting the putty all over the place all at once. And then you can shape it. But we cannot sprout so many arms. So what do? We sort of poke it one place at a time. And when you do that, when you push things down at one place, they pop up at another place. And you have to be really skillful at making sure that you make all of these adjustments. And what is the key to doing that? If you're going to do this, just poking your putty one place at a time. You make those adjustments really small. You have to be very, very careful. And so that's basically what we will do. You're going to adjust the function at one training point at a time, keeping the adjustment small. You pick a location, you push it up a bit. Then you go to another location, push that up a bit. Then you come here the function is overshot, you push it down a bit. And then pick yet another location, now the function is under computing, push it up a bit. So one location at a time. You can just keep doing this. And eventually, you would have processed all of the training samples. And if you do this right, you can actually have adjusted the entire function with greater adjustment than if you've done a batch update, where you looked at the entire training data before you made a single update. So here is what the incremental update process was. Earlier, when you did a batch update, you'd have to go over all of your training samples and compute the average gradient over the entire training data before you made an adjustment. Now, you just go through your training data, and at each point, you just compute the derivative of the divergence for that one point and make an update instantly. Now, this doesn't mean that you just make one pass over the entire training data. You can actually do this again and again. You pass over the entire training data, you make all of your little updates, then you go back and do it again. So the iterations can make multiple passes over the data, and a single pass over the data is what we call an epoch. You're familiar with this term. So an epoch with a, yes?
Professor, wouldn't this result in overfitting?
Would it? So again, think of the putty here, think of the putty example. You're still trying to function, you're still trying to shape the putty into some landscape or a doll. Are you going to adjust every single point, all the infinite points on the putty, or just some subset of points?
Got it. Thanks, Professor.
Right? So it's a nice metaphor to think about, shaping clay. So an epoch with a set with t samples results in t updates of parameters. We'll get back to this question. We'll discuss this in some detail in this class and the next. So here's what we are doing. Every time, so we can do this many times. And each time you do it, it's one epoch. And within an epoch, you're going through all of the training data samples. And each time you look at a sample, you're making an adjustment to the function. But then you can't just do this naively. Here's any of you who's actually played around with putty, and almost every one of us has in kindergarten. You can't just keep poking at the same point, right? It's not going to work out. Now, functionally, in terms of functions, let's look at a toy example. Now, anytime you have a function, anytime you have a network or any characterization of a function, it has some inherent limitations on what it can model. So let's just assume over here that the function I have has this light curved shape. And now I want to adjust this function to compute these, so that it best computes these 4 samples here and these 4 samples here. So the target values are all on the dotted line. The vertical lines are just showing you where they lie, right? So if I start from the left and I begin pushing the function, correcting the function at the left, by the time I'm done correcting all 4 samples at the left, the function is going to pop up at the right. What would happen now if I go to the right and adjust those? It's going to pop up at the left, right? And then if I go back to the left and I adjust those, so it's going to go back and pop up at the right. Will this ever stop? No, right? So what would be the solution to this? You want to do this randomly because there's no notion of left or right and high dimensional spaces. And so we want to go through the samples. If you loop through the samples in the same order every time, you are almost certainly going to end up with cyclic behavior. So we want to go through them randomly. Maybe pick one sample up here and push it down, then pick one sample here and push it up, and so on. And so long as you are doing this randomly enough, eventually it's going to adjust and give you the best fit to the data that you do have. So if you go back and look at how that changes our pseudocode, within each epoch, before you go over your data, you want to permute your data randomly. Now, picking up a random data point is the same as permuting your data and going through it sequentially. So, because you're changing the order each time. And so within each epoch, you want to randomize the order of the training samples before you go through them. And so the story so far, in any gradient descent optimization, presenting training data instances incrementally can be more effective than presenting them all at once, in principle, provided the training data instances are presented in random order. And this is the technique that we call stochastic gradient descent. The term stochastic literally means random. And so arises from the fact that we're presenting the training data samples in random order. And then you're performing gradient descent. So this is for any kind of minimization, function optimization. In this case, we are applying it to training neural networks. So why and when does the process of incremental updates work, and under what conditions? So for the why, let's consider a very simple example first. And I'm going to look at a very extreme example. First, what exactly are we doing? When I have a bunch of training data, the error at each training instance is different. So the effect of adjusting the parameters is going to be different at each training instance. And so if I have in my multidimensional space, if this is the current location of my estimates, then the error, the effect of adjusting these parameters is going to be different for each of my training instances. In one case, the gradient may say going this way will reduce the error. On the other training sample, it may say that going this way will reduce the error. So each training sample has its own different favorite direction for adjusting the parameters. And what we do is to find the average across all the training samples. And that red direction is the direction that we're taking a step in. But now, consider an extreme case where all of my training samples are the same. Here, are all these divergences going to be different for the training samples, or are they all going to be the same? They're going to be the same, right? So would it make sense for me to go through all of my training data samples to compute my average divergence? It does not, right? Because if I look at this, all of my training data samples have the same divergence. The average is also going to be the same. And so when I begin making adjustments, when I'm performing a batch update, eventually I'm taking the average divergence over all of the training samples. It's like adjusting my function by one little bit, like so. Whereas if I made an adjustment after every single training data point, even if the actual adjustment size is smaller, in a single pass through the training data, I'm going to be modifying the function a whole lot more. So you're going to get much greater net adjustment in one pass through the data. Now, this is for the extreme case where all the training data samples are exactly identical. But instead of being exactly identical, if all of them were perturbed a little bit, would this change the picture a whole lot? Like, say this. Would this change the picture a whole lot? No, right? So as I make them more and more diverse, the benefit you get from just incrementally adjusting parameters is going to decrease. And at some point, it's probably going to vanish when the data points are sufficiently random. But still, you get some benefits and some benefits in terms of computational ease. So that makes sense to everybody? And so what are the considerations, more formally, for when it will work and how well does it work? For this, let's take a look at another issue. And here, in this case, I like to have simple illustrations. Let's say I have this bunch of training data points shown by the black dots, and my model is trying to fit a straight line through origin to these training data points. Now, I start off with some initial estimate, and I'm trying to find the line that minimizes the total error across all the training points when I fit it. So it's the average length of those perpendicular drops onto the line. Now, if I start off with my first training data point, what is the best line for that point? It's going to go straight through the line, right? And then I pick up the next one. And the line is going to swing over to this next point. And then I pick up the next one, and it's going to swing to that one. Will it ever stop? Right? It's always going to be chasing the latest training data point. This process will not converge. So given this, right, this guy here, this picture is very optimistic, but this is really not what is going to happen, right? So how would you resolve this? Anybody? Mm-hmm.
Take multiple points and take the average of the loss.
Take multiple points and take the average of the loss. How would you resolve it?
Same.
Same. Anybody else? Yes.
When we update, don't be so extreme as to completely change the line to go through it. Just a little bit more in that direction.
But will that ever make it stop bouncing around?
Is the rate at which we adjust decreases over time.
Thank you, right? This is basically what we want to do, right? The solution is update the model, but as you go through the data, you're beginning to trust where you are more and more and more. And so initially, maybe you just go through the point. The next time around, you have a large error, you swing towards it, but you don't go all the way to the point. The next time around, you swing even less. And so long as the corrections you make keep decreasing with iterations, eventually the corrections are going to be small, and the function you learn is going to stabilize at something that maybe minimizes the overall divergence. And so in the incremental learning, you want the update model to always minimize the error on the latest training instance. This is what we are doing. But then we must shrink the learning rate with iterations for convergence. And so the correction for individual instances with the eventual minuscule adjustments will eventually not change the function too much, and it will stabilize, hopefully, to something that makes sense. Did that make sense to everybody? Okay. So here is what here's how it would modify your pseudocode. Again, over the epochs, the first thing you do is to randomize all of your data. This is essential. And secondly, the learning rate with which you adjust your parameters has to keep reducing as you go through the steps. So what is the rate at which this learning rate must converge? Do we have any considerations, restrictions on the behavior of the learning rate itself? So here it is. If I keep going through this, my learning rate is being modified in some manner. So I have a sequence of learning rates, eta I, which may be 1.9. It's a series that keeps changing with iterations. So let's look at an extreme example. Let's say this is my optimal value for a parameter. So in the parameter space, that's my optimal value. And let's say this is my initial parameter. Now, the derivative of the loss with respect to the parameter has some value, right? Is it ever going to be infinite?
No.
No, we designed our loss and our activations to ensure that these derivatives don't blow up, right? So let's say I have a maximum value for the derivative. And so if the largest value for the derivative is some c, then in how many steps, what is the smallest number of steps in which I can get from point A to point B, if this distance is d? If this is d, what is the smallest number of steps in which I can get from point A to point B? D over c, right? But really? What is the actual step size using this rule? The actual step size is going to be eta IC, correct? So what is the total correction you're making over infinite steps? It's going to be summation I eta IC, right? Which is going to be C times summation I eta I. This is the maximum amount by which you're going to be able to adjust. You cannot adjust more than this, right? And this has to be greater than or equal to the distance d, right? Now, what is the largest value for d? You can't say. You can be infinitely off, right? Yes or no, right? So, and d can be as large, or let me just call this equals, just to make things nicer. But d can be infinite, right? C is not infinite. C is finite. So what does this tell us about the summation of the step sizes?
They should be able to be,
Yeah?
they should be able to be infinite.
They should be able to be infinite. It's some sequence of step sizes. So what does it tell us about the sequence of step sizes, guys? Yeah? Shouldn't go to zero, but it shouldn't go to zero and sufficient? Can I multiply C with any, so we know that D can be as large as infinity, right? C is finite. Can I multiply C with any finite value and get infinity? So what must this be? This must be infinite also, right? So in other words, your step sizes may be shrinking with iterations. Nonetheless, it cannot be a convergent sequence, right? That makes sense to all of you? And the reason for this is that if it converges, then there are situations where you're never ever going to get to your optimum. And so you have requirements on your step sizes. The sum of the step sizes must be infinite. But then the easiest way to make the sum infinite is to make them fixed. But that's not a nice thing, right? You want the step sizes to shrink. So how do you encapsulate that? The sum of the squared step sizes must be finite. So can anybody give me an example of a series where the sum of the series is infinite, but the sum of the squared sum values is finite? Yes?
1 over x.
1 over x, right? The harmonic series. What is, we know that 1 over x, 1 over n is divergent, 1 over n squared is convergent. Right, so this, it turns out, is actually at the very border. It's 1 over n raised to any alpha greater than 1 is going to be a convergent series. But 1 over n raised to any alpha less than 1 is going to be, less than or equal to 1 is going to be divergent. But then, you know, it's going to be, in terms of square summation, it's not going to be converging fast enough. And so 1 over n is kind of the optimal sequence of step sizes, which ensures that over an infinite series, it still sums to infinity, but it's square summable. There's a very nice paper on this. And so if the loss is convex, if you follow these properties, the stochastic gradient descent algorithm will converge to the optimum. For non-convex functions, it's going to get to a local optimum. And in fact, all of the learning rate schedulers that you have when you work on your homeworks are going to have this property that in the limit, they are going to sum to infinity, but you know, they're going to be absolutely divergent, but square summable. Now, you don't really need to have something that goes down as 1 over n. You can actually have something which goes down this way, and it has the same property. So typically, this is what we use, right? Any questions? Yeah.
Like, why in practice you use stuff like exponential decay?
So in practice, you're never actually going to go all the way to infinity. And so we're depending on some of the actual practicalities of the problem itself. But in the worst case, that won't get you there, right? So let's see how well this behaves. This is an example I pulled off the web for k-means clustering. And you know how k-means clustering works. You have a whole bunch of data. You have to cluster it into a finite number of clusters. And depending on how you initialize it, you're going to get different solutions. So over here, you know, as you go through the iterations, the optimality of your solution is going to change. And so this was the actual solution for k-means. Regardless of the initialization, after if you've spent 1.5 seconds on this particular data, the range of solutions you get have this variance and the squared loss. And by the time you get to 100 seconds, all of them end up at the same point. So you can see that the solutions, the training converges across the different runs with iterations. The vertical bars show you how much the loss value varies across different runs. Now the red one is exactly the same thing, but for stochastic gradient descent. And which one converges faster? Which one gets to its flat value sooner? The red one, right? Because the x-axis is time. Before the batch value even begins its descent, the red one has already flattened out. So stochastic gradient descent actually converges much faster. But has it converged to the same loss? It's converged to a much, much, much worse loss. And this is something that we will actually encounter. So why does this happen? Well, we will see in a minute. 90 seconds, please. Okay, I think we've used our 90 seconds. Can someone on Zoom tell me if that first statement is true? Anybody on Zoom?
Yes, that's correct.
Correct.
Okay, what about the second one?
Correct.
Third? What about the third
Correct.
and the fourth?
Correct.
Okay, all of them are correct, right? Stochastic gradient descent is an online version of batch updates. It can have oscillatory behavior if you do not randomize the order in which you present the inputs. And it can converge faster than batch updates, but arrive at a poorer optimum. And convergence can only be guaranteed if the step sizes shrink with iterations. And there are minimal requirements for how the step sizes may shrink. If they don't satisfy that, then your learning might never converge, right? So now let's go back to why this difference and how we can fix it. Yes, Hector.
Wait, sorry, for the fourth option, don't we also need the function to be convex?
Not necessary. It's going to converge to a local optimum, just so long as the gradients are finite. Actually, it turns out that you can, if you satisfy this property, it will converge to a global optimum for, if your step sizes go down slowly enough, then there are guarantees that it will go to a global optimum. Otherwise, it's going to go to a local optimum. Again, assuming that your function satisfies certain minimal properties. So it's actually a very nice result. Going back to the 50s, I think, or 60s. I should post a link. Okay, so now let's go back to our function again. Here's what we wanted to minimize. What we wanted to minimize was the expected divergence. The expected divergence is this area, the shaded area. But what we are actually minimizing is the average divergence over the training data, right? So now let's look at this. The input has some distribution. And so now if I have, say this is my target function, G, and my chalks went away, yeah.
It's on the desk. The orange chalk is on the desk by your eraser.
Oh yeah, thank you. I also found my pink one. So if this is my function f, now if I randomly choose a sample, then on any randomly chosen sample, I'm going to get a divergence, right? If I keep randomly choosing samples, what is the expected divergence? So this expected divergence that I was showing was basically telling you what this, that if I keep randomly selecting samples from my training distribution and then compute the average divergence over all of these, that is my expected divergence, right? And so the expected divergence of x is basically what we're trying to minimize. This is the expectation. But then, is it always going to be the same? Is the divergence going to be the same at every point? No. So it's also going to have a variance, right? So the two characteristics for this are going to be the expected divergence and the variance of the divergence of x. Now, if I look at this guy, if I look at 1 over n summation I, divergence of x of I, which is my loss. If I take the expectation of the loss, meaning if I say I have a whole bunch of points, I'm going to compute their divergence, and then I average it. And if I repeated this experiment lots and lots and lots of times, what is the average loss I would get? So this is my loss. And the actual value of the loss is going to depend on the set of training points I choose. So the expected value of the loss is going to be, by the linearity of expectation, expected value of the divergence of x of I. Each of these is a random sample. So what is this going to be? The expected value of any time of the divergence of any random sample is just the expected value of the divergence itself, right? Which is going to be just the expected value of the divergence of x, which is exactly what you had over there, which is why we like to do this. Because in expectation, our loss is basically what we want to actually minimize. We sort of believe that minimizing our loss will also minimize the actual objective. But then, what is the variance of the loss? What do I mean by the variance of the loss? If I chose a different set of training points, I'm going to have a different loss, right? Each time I choose a different set of training points, I'm going to have a different loss. So the loss has a variance. What is the variance of this loss? Now, here is a property. If I have x1, x2, and so on, if I have a bunch of different independent random variables, then the variance of x1 plus x2 is going to be the variance of x1 plus variance of x2. This is an easily shown property. I'm not going to show this, but the variance of the sum of independent random variables is going to be the sum of their variances, right? So what is the variance of the average of two independent random variables? Yeah. So if I take the variance of the average of two variables, which is variance of x1 plus x2 over 2, that's going to be 1 over 4, because variance does the squaring of variance of x1 plus x2, which is going to be 1 over 4 variance of x1 plus variance of x2. Everybody with me? And if x1 and x2 are identically distributed, then this is simply going to be, if I have half variance of x. So in general, if I have n training points, if I have n samples, what will the variance be?
1 by n.
If I have n samples of this kind, for variance of the loss of n samples is going to be 1 over n, the variance of the divergence of x. This is what we get for our training data. And so the expected value of our empirical risk is actually the expected divergence, which we actually want to minimize. So the empirical risk is an unbiased estimator, meaning that on average, over many different training sets, you're always going to get the average of the loss that you'd get over different training sets is going to be the actual objective that we want to minimize. So it's an unbiased estimator. But then across different runs, it's going to have different losses. And so the variance of this guy is going to be 1 over n, the variance of the divergence, and n is the training set, size of the number of training points. So as you keep increasing the number of training points, the variance in the loss across different runs decreases. Now, if I'm looking at SGD, right? So here's what the variance of the loss is going to look like. Variance of the loss over number of training points. So at 1, this is going to be just the variance of the divergence. We saw this, right? And then it's going to come down like so as n increases. So when I'm performing SGD, I still have the same point. I'm looking at the divergence for a single point. The expected value of the divergence at a single point is simply the shaded area, right? The expected divergence. So this guy too, the sample divergence, is also an unbiased estimator, or estimator of the expected error. But the variance, meaning how much this loss changes from sample to sample, can be huge. So if I have a very large training sample, the variance of my loss is going to be somewhere out here. Whereas if my training sample is just a single one, my variance is going to be out here, which is why when I train across different runs, when I'm performing stochastic gradient descent, my loss values are going to be bouncing all over the place, and things don't converge. Now, maybe the math doesn't make a lot of sense, but pictures do. So the blue curve is the function g that we're trying to approximate. The red curve is the function that's currently being computed by the network. And the divergence is going to be the difference between the two. We are trying to minimize the shaded area. So let's say I have a small bunch of training points. If I have these training points, these 5, 6 training points, these training points are telling me that the function must go up here, it must go down here, it must go down here, it must go down here, and it must go up here. Right? Anywhere, anytime the function is below the target, it has to go up. Anytime it's above, it must go down. Right? On the other hand, if I chose this set of training points, a completely different set of 6 training points, it's going to tell me that the function must go up everywhere. Is that correct? There are places where it must go down, right? On the other hand, if I had these as my training points, what does it tell me? That the function must go down everywhere. So the kind of adjustment you make is going to be dependent on the specific set of training points you choose, which is why you have so much variance between, what you get when you change your training set. So what would be a good thing to do? How do you minimize this fluctuation? Yeah.
Take the large sample.
Just have a very large training set, and you're going to, and then variations in the training set are not going to result in large variations in the loss and the behavior of the loss with change of parameter. That makes sense to everybody? Right. On the other hand, if I have only one sample, if my sample ends up there, it's just telling me I'm fine. If it's here, it says you've got to increase the function. If it's here, it says you've got to decrease the function. And so the behavior can change wildly because you're always looking at only one training point, which explains this picture. When you're working with stochastic gradient descent, at each time you're looking at only one training point. So the loss is going to swing wildly from sample to sample. Whereas when you're performing batch descent, you're getting consistent estimates every time, which is why although SGD will converge quickly because we made our learning rates shrink and all the other things, it can converge to a nasty location. So is there something that you can think of that gets the computational benefits of SGD, but not the nasty tendency to go to wrong places? Not multiple points, but not the whole class, right? Whole set. So SGD uses gradient from only one sample and so has high variance, but provides significantly quicker updates than batch. So is there a good medium? I can pick random samples. Instead of picking one sample, I pick a set of samples. And so maybe in my first step, I pick these 3 samples and make adjustments, which gives me a new function. Then I take 3 other samples and make my adjustment, and then that adjusts my function, and so on. I can keep doing this. So here's what, does that make sense to everybody? Right. And so here's what that behavior looks like. Now, you're going to be, within each epoch, you're still going to be permuting your data, regardless of whether you're adjusting it one sample at a time or a small mini batch at a time. You don't want cyclic behavior, so you must randomize your the presentation of your data between epochs. But then within each epoch, you're going to be operating on mini batches of instances and adjusting after a mini batch. So if this is the case, what can you tell me about what is an optimal mini batch size? Anybody?
It should be good enough to represent the data.
So here is what you get. If n is your actual total training data, then the variance of the loss is proportional to 1 over n. So if you have a billion training points, the variance of the losses is very close to, is proportional to 0. It depends on the expected, the variance of the divergence itself, right? So you want your mini batch. What is the variance of the mini batch, of the loss for the mini batch? Anyone?
1 over the size.
So for the mini batch, again, the expected value of the mini batch, again, this is it's an unbiased estimator. The expected mini batch loss is the actual function you're trying to minimize. But the variance is going to be 1 over b. So as you keep increasing the mini batch size, the variance of the loss from sample to sample keeps decreasing, right? And so if you have a mini batch size of 1, that's your variance. If you have a mini batch size of 2, that's going to be 2, right? At some point, your mini batch becomes large enough that this difference is not very much. And so you want the mini batch to be as large as you can possibly fit into your compute, because that minimizes the variance of the loss between mini batches. Make sense to everyone? Right. So here was on that previous example, this is what the behavior looks like with mini batches. And you can see how it consistently converges. It converges to a loss that is very close to what you would get if you actually use your entire training data. You still have more variance because the mini batch size is smaller than your entire training data. So it's going to fluctuate, but not as much as SGD. And where it converges to is also going to be pretty close to where you would converge to using the entire training data, but it's going to converge there as quickly as you would if you were using stochastic gradient descent, right? Again, the difference is SGD is using one sample at a time. Mini batch descent is looking at small collections of samples. And so again, we are speaking, the convergence over here is defined in terms of overall training loss on the entire training data. All the plots that you plot in your homeworks, they are bogus. Every last one of them is bogus because you are plotting the loss on the latest mini batch. What is it that we are looking guaranteed convergence for? The loss on the entire training data. You're just sort of getting some guess at it. Still, you expect that to converge, right? That makes sense to everybody? Yeah. Okay. So in practice, training is usually performed using mini batches, and you would like to set it to the largest that your hardware will support without compromising overall compute time. Larger mini batches is less variance. And also, larger mini batches means fewer updates per epoch, which is also a convenient thing. Convergence depends on learning rate. Again, even if you're working with mini batches, the learning rate has to shrink with iterations. This is a requirement. And so we have various techniques like fix a learning rate till the epoch error plateaus, then reduce it, and so on. We have adaptive updates, where the learning rate itself is determined as part of the estimation. But anyway, here's a poll. Okay. I think most of you must have read it by now. So, Jun Kyung, is the first statement correct or false? True? You in the corner. What's your name?
Bennett.
Bennett, okay. So was the second statement true or false?
I think it's true.
I think it's true. Terrence, what about the third?
True.
And you? What about the fourth? Also true. May I know your name?
Alan.
Alan. Thank you. Guys, get your name tags out in future so I don't have to ask you your name, right? But it turns out the second one cannot be true, right? SGD is not mini batch descent with a batch size of 1 is exactly stochastic gradient descent. And so the second statement is false, everything else is true. Mini batch descent is also an online version of batch updates, except you're updating things after seeing batches of instances. And with vector processing, that's going to actually be much faster than SGD. So the story so far, presenting training instances one at a time can be more effective than full batch training, provided they are presented in random order. Should be. For it to converge, the learning rate must shrink sufficiently rapidly with iterations. Otherwise, the learning will continuously chase the latest training instance. And SGD estimates have higher variance than batch estimates. Mini batch updates operate on batches of instances at a time. So because they operate on batches, the estimates have lower variance than SGD. And so in theory, the convergence rate is actually worse than SGD. But then convergence is one thing, converging to the right, a good solution is a completely different thing. And so, because we're able to perform batch processing, you can still get benefits, with GPUs and such like, and you can get to a better estimate than you would with just SGD. Now, there are problems where SGD will give you a better solution than mini batch you will encounter at various points in your life. But anyway, so moving on, any questions?
Yeah, on the whole, what does online mean?
Online is as data comes in,
Okay.
right? So we think of it as streaming. So you could literally be just updating the models as data keeps streaming in. Right. Yes.
What was the vector? What do you mean by vector processing?
So vector meaning we're processing large amounts of parallel processing graphics. It's just a standard term. So when you're operating with GPUs, you're processing many different instances all at once, right? So, or many components all at once. Again, terminology, but you get the concept, right? Okay. So now, here's another thing. Let's go back to this business of trends. We briefly discussed trends in the last class. It turns out these are very important. Figuring out, so one, and particularly when we're working with things like stochastic gradient descent or mini batch descent. Sorry, guys. It's what happens is because your mini batches are changing from iteration to iteration. Each time you pass through the data, you're working on a different mini batch. You're working on a different sample. So even when you're performing standard gradient descent, we know that the direction in which the divergence points can keep bouncing around. When you're working on a completely different set of samples each time, this fluctuation is going to be much, much greater. So we would like to be able to deal with these, and we run with all the standard convergence issues that we end up with when we are looking at batch updates. And so we need to compensate for that as well. We use the same principle as before. Now, if I'm going through my data, then in parameter space, at some point, let's say this is my gradient, and that's the resulting step. I have a step size, right? But let's say this is my gradient in the current, on my current sample or mini batch. Then I'm going to go here. Let's say this is my gradient on my next sample or mini batch. And then this is my gradient on my next sample or mini batch. What are we observing? We're observing that the gradients are kind of consistent along the horizontal direction, and they are terrible along the vertical direction, right? So how can I sort of try to compensate for it? A lot of work that goes on dealing with this kind of fluctuation, where in some components, along some directions, they are consistent. Along other directions, they are bouncing around. Now, here, if I were to take an average of all of these guys, what is the average gradient along the horizontal direction?
A little bit to the right.
It's going to be a little bit to the right, right? So over here, this first one is going to be at step one, it's going to be this much. At the second step, it's going to be this much. At the third step, so every time it's going to have the same direction. What is the average gradient in the vertical direction?
Close to zero.
It's going to be close to zero, right? So it makes sense. If you begin looking at average gradients, that gives you a much better notion of which way you want to go. And this is particularly relevant when we're working with mini batches or single instances. If I look at the average gradient over the entire training sample, I'm going to get a gradient that's much closer to the gradient for the batch. But then, again, we don't want to wait all the way to the end to figure out what the average gradient was. And even that gradient can have random perturbations and fluctuations. So what would be a good thing for us to do? So again, thinking of it purely in terms of online, if I want to compute the average gradient over the entire batch, but then I want to keep updating it, what would I do?
Keeping the running average of everything.
Keep a running average, right? So what I would do is something like this. I'm going to have this one. This is going to be my gradient, sequence of gradients over all of my iterations, all of my mini batches. What I want to do is to compute the average of all of these guys. There are two purposes for this. First, computing the average over the epoch gives me something like the average gradient for the entire batch. But then even apart from this, if I were just considering batches at a time, gradients which bounce around tell me that at the, like even in this trivial problem that I show on the board, tell me that in some directions those gradients don't make a lot of sense, in other directions they do. And so we want to compute the expected or the average delta W. But then you can't wait to compute the average delta W before you make an update. So what we will do is to maintain a running estimate. I'm going to say that average K of my delta W is going to be, there are different ways of maintaining a running estimate, right? So the most standard one is going to be some alpha times average at step K minus 1 of delta W plus 1 minus alpha for the kth step, right? This is the standard mechanism for maintaining running averages. And so if you just maintained a running average of this kind, then at each step, the actual correction you would be making is going to be with the current running average of the gradient. I see some frowns. Does that make sense? Right? Are you sure? Yes, okay. So what did I say? The lady there. You guys are looking confused. So I just want to make sure I haven't missed this. I have a couple of minutes. So what? Can you explain it back to me?
So with the weighted sum here, it's kind of maintaining the average.
It's maintaining a running average, right? And it's very easy to show why this running average works. If I have n samples coming in, then 1 over n, or the k samples, 1 over k summation I, I'll just call this is my divergence di. This is my average after k samples, correct? The average after k minus 1 samples was 1 over k minus 1 summation I equals 1 to k minus 1 di. So I have two different formulae. If I write this guy in terms of this one, then I can say average k equals k minus 1 times average k minus 1. Basically, it got rid of this division, which is just the summation, plus the dk over k. So I just scaled out the k minus 1, then added in the new instance, and divided by k, which looks like k minus 1 over k, average k minus 1 plus 1 over k dk, right? Which looks like alpha times average k minus 1 plus 1 minus alpha times dk. So you get the idea, right? I mean, if I did it right, that alpha is going to change with the number of samples, but this is a simpler way of looking at it. So the running average is a very easy way to, yes?
So this formula over here sort of weights all the previous gradients equally. Don't
Yes.
you want to weight like the most recent ones more?
No, you don't. So I mean, you're just running, so you're maintaining a running average. So this one over here will, if my actual alpha changes with k, that's going to be weighting all of the samples equally. If I have a fixed alpha, that's not going to be the case. The most recent one is going to get more weight. It's a good point. But anyway, so this is basically what we're going to do. we are going to maintain a running average of the gradients. And so a different way of thinking about it is that, now, what is the step we took at any time? The step we took at any time was proportional to the running average of the gradients until that time. And so I can just say that I am using what's the time? Okay. So I'm using, let me call this delta W as the step. K is going to be some beta times delta W of K minus 1 plus alpha times delta W of K. So this is basically saying that this is the latest gradient, actually. So this is the latest gradient. And you're just taking the step size, because the step size that you took was actually encapsulates the running average of the gradient until that point. And then you're just summing in the latest gradient. And that's what you would be doing to adjust your, come up with a new update. This minus is simply because you're taking a step against the gradient. And so this is what momentum methods do. You maintain a step size, and the current step size is a weighted sum of the last step that you took and the latest gradient. And this is the new step that you're going to take. That makes sense to everybody? Right. And so typical value for this, you can see this, it's going to be some beta times the previous step size minus the learning rate times the current step size. If this is what...
If you get a chance, I sent you that stuff for Purdue. If there's anything in there
Guys,
that's like.
I don't know, I don't think you're speaking to me. Can you mute yourselves?
It looks like when I went
Can we
on
mute Zoom,
there
please?
that was from my daughter.
Hello, guys
I
on
don't know if
Zoom?
it looked like the
Paul, can you
math
mute
club
Zoom?
and the stats club were two of the
Andrew's
bigger
iPhone, can you
ones.
please mute?
Maybe we just
Paul?
reach out to both those, but if you know somebody in particular, you should put a couple professors.
Thank you. Guys, when you're in class, you're supposed to be attending class. I don't know what conversation you're having. I don't care what conversation you're having. Please switch off your Zoom. We'll mark you absent, and then go and have your conversation outside. Okay. So, all right. Did this make sense to everybody? And so again, this has this property. When I maintain a running average, then the running average is going to cancel out the swings in directions where the sign keeps changing wildly. And it's going to emphasize the steps in directions which aggregate. So this has this natural property even for batch updates. In the case of mini batch and stochastic gradient updates, it also has the property of approximating the batch gradient. Yes, Imaj?
Wouldn't it result in a cold start problem? So let's say with the initial samples of our data, the loss was less, and due to which the gradient wasn't of very high magnitude.
No, so the value of the loss has nothing to do with the gradient. The gradient you can have a loss of 0 and a very steep gradient. So it won't be a problem. Okay, now, so here's what the gradient update does. The momentum update does. Let's say this was the last step that you took. Then you have a gradient at the current location. And taking a step against the gradient is actually making you walk along the blue line, right? And then to that, you're going to be adding a scaled version of the last step that you took. And this is the actual final step that you take. So look at the order of operations. First, you've taken a step, then it's like taking a step against the gradient, and then taking a step that's a scaled version of the last step that you took. There are two steps over here. The first is the step against the gradient, and the second is the step that's proportional to the last step that you took. I can change this order. Instead, so that's 1 and that's 2. Instead, I can do this. I can first take a step that's an extension of the previous step, and then take a step against the gradient. I'm performing the same two operations, just in different order. And that's going to get me to a new point. This was Nesterov's accelerated gradient. And Nesterov's, so the formulae are over here. This is like saying I'm going to be extending my current step and computing the gradient at the new location. And that is the correction that I'm going to be taking from that new location. So within each step, you're still performing the same two steps, but then the order is different. And it turns out that this is actually much more optimal than standard momentum updates. Here's a picture from Hinton. So for example, if this were your last step, if you're doing a momentum update, this would be the gradient, and then you're doing a scaled version of this step. Whereas if you were doing Nestrovs, you do a scaled version of that step and take the step down. And as you can see, Nestrovs gets to the solution much, much faster. It's provably more optimal under some conditions. So I tried reading this paper a long time ago and convincing myself. And the first statement said, obviously blah, and made some mathematical statement. Then I couldn't understand it. So I took it to my student who had won a math Olympiad. And so he spent a full day on it and then came back and explained to me why it was obvious. So, but yes, it's a fantastic algorithm. And once again, this gradient is going to be computed using, that's the SGD instance of mini batch loss. And the derivative is going to be computed using backprop, both for momentum updates and for Nestrovs accelerated update. All right, so here is now, so what happened over here? This is your standard gradient descent rule. You have some initial W, and then you took a step against the gradient. The step was some learning rate times the gradient, except that the gradient that you used was no longer the latest sample gradient. What did we use? The running average. That's what we used, correct? So, but there's another thing over here that you can also, that's also under control. What is that? Eta, the learning rate. So the momentum methods fix this term. But then there's the second term, right? Now, how does that affect things? Consider these three examples. In all three examples, the running average in the vertical direction is the same. It's just that the swings are much greater in the rightmost example than in the leftmost example. So would you still want to be following the running average of the gradient with the same learning rate in all three cases? Yes or no? What does intuition tell you?
Smaller steps, more varying more.
But smaller steps where it's varying a lot because you trust it a whole lot less, right? So how can I quantify the fact that although the running average is the same, I've swung around a whole lot more? I can look at the variance, I can actually look at the length, right? Except if I just look at the length, sometimes it's up, sometimes it's down, so I can just take the RMS value, how much the length is. And so this is basically what we do. This is RMS prop. We keep track of the squared length of the derivative in each direction. And then we compute the mean squared length of the derivative. And the mean squared, so here is what we would do. We're going to keep track of the mean squared length of the derivative. And now the learning rate is simply going to be inversely proportional to the mean squared length or root mean squared length of the step in that direction. Now observe what has happened. The learning rate for each component has changed. You're no longer having a component-specific learning rate. This is going back to what we discussed in the last class. And so this is going to converge faster. And also note the similarity to RProp, meaning if you're walking along a constant slope, then the derivative is going to be constant. You just have a constant step size, right? We are basically, moreover, if I'm walking along a constant slope, this term, the squared magnitude, the square root of the squared magnitude is just the magnitude. These guys will cancel out. You're just always taking a constant step, regardless of the slope, just like an RProp, which is why it was called RMS prop as an extension of RProp. So RMS prop only adapts this learning rate by total movement. We have two different things here. RMS prop adapts eta, and it adapts eta to be inversely proportional to the RMS value of the magnitude. Momentum methods adapt only the gradient. So knowing this, you as smart young people, what would your next step be? Combine the two, right? If I combine the two, that gives me Adam. So this is literally just this. Adam is a combination of RMS prop and momentum methods, where I'm maintain a running average of the gradient, that is this M over here. I also maintain a running average of the second of the squared derivative along each component. And the actual update rule is going to be using the running average of the gradient as my direction. And component-wise, so this is going to be changing by component, I'm going to be using the RMS value as the inverse of the RMS value as my step size. Or the step size is going to be inversely proportional to the RMS value of the component. There's one extra magical term over here, 1 minus gamma raised to k, 1 minus delta raised to k. What are these things? It turns out that typically all values are 0 and in the beginning. So in the beginning, if you do this carelessly, then you're going to get stuck. You don't really make any updates. And so you have the scaling factor, 1 over gamma raised to k, which says that these estimates are going to be scaled by a term which which starts off close to 0 and then quickly becomes 1. So the scaling factor disappears, yeah.
Are we resetting these values after each epoch, or is it running through the entire?
You just run through, right? That's it. Because the step sizes are automatically figured out, right? And so you don't have to deal with optimizing things anymore. So typically mu0 is going to be 0 and delta is close to 1. So 1 minus delta is close to 0. So typically if mu0 were 0 and you did not have this denominator term, then you're going to find that the running average is simply always going to be the latest sample, right? Or just going to stay close to 0. So you don't want this. If delta were 1, then this becomes 0, this becomes 1, and the mean will never update. And so you have this delta raised to k. And now, once you get the general hang of this, you get the general idea of these various optimizers. What are the optimizers doing? A, they are maintaining running averages of the gradients for two purposes. One, maintaining a running average approximates batch updates better. Second, it's going to eliminate oscillations in nasty directions. The other thing they do is to adjust the learning rate, and the learning rate is adjusted to account for swings. Directions in which you have wild swing will have lower learning rates. In other directions, you're going to have higher learning rates. And so here's a poll. We'll stop with the poll. There are some examples on the slides, which is of how these different things behave, optimizers behave on different functions. We can take a look. You can find these online too. Okay, guys, for this one alone, I'm not going to give you that much time. Can anybody tell me if the first term is right? No. Second one. Third. Third, true or false? Fourth. And the fifth? Yeah, so only the first statement is false, right? And here are some examples, pictorial examples of how the different optimizers behave. It's kind of pretty. And you can actually look at, here's a crazy one. See, look at how SGD basically gets stuck in the saddle. And RMS prop generally tends to be very stately when it hits a steady slope, because the derivative terms cancel out and all you're left with is the step size, but the rest of them behave differently. But eventually, I think Nestrov's method actually tends to be the fastest to get to the optimum in most cases. But in many cases, Adam's just better. Yeah. They do, right? They do. Anyway, let's stop. Thank you very much, guys. The next instructor is going to be here any moment. I appreciate your time.